Hi everyone. We finally get to the video that explains what is going on this cover sheet, because it looks like here we have nitrate, NO3 minus, represented by three different structures. Not only that, we're showing the movement of electrons to make these three different structures. That's due to resonance. So resonance is a situation, or you could say that a molecule undergoes resonance when more than one Lewis structure is a good description of what the molecule is, or more than one Lewis structure represents that molecule. Now, I know what a lot of you are saying. A lot of you are saying, well, aren't those three just the same drawing, just rotated? They look like that, but resonance, you have to keep all the atoms still. So let me show you that example, the nitrate example. And we could say that NO3, the terminology is NO3 undergoes resonance. Undergoes resonance. So what does that mean? It means that if a molecule undergoes resonance, it means that more than one Lewis structure can be used to represent it. And those structures are valid. Maybe we should say that more than one valid structure, Lewis structure, can be used to represent it. The other thing is that resonance is a stabilizing effect. Resonance, is a stabilizing, sorry, stabilizing effect because it's called delocalizes. It delocalizes electrons and often charge. And often charge. Okay, so we have a couple new words. We have undergoes resonance, valid Lewis structures, stabilizing effect because it delocalizes. Remember, in several videos, I mentioned that a molecule really wants to minimize the number of atoms that are charged. A lot of times when we have a molecule that has multiple charges, we can move electrons in such a way that we can make some of those atoms neutral. And that's typically a stabilizing effect. And that's typically leading to the most valid Lewis structure. Let me show you nitrate. So nitrate, it's a little bit unusual because the central atom is charged, and I'll draw it. Let me draw it like this. Okay. We have a double bond here, two lone pairs. Three lone pairs negative, three lone pairs negative, and this nitrogen, remember your formal charge equation? Valence electrons minus sticks plus balls. There are no lone pairs on this nitrogen. The nitrate is that. It has the right number of valence electrons. Nitrogen satisfies the octet rule. It has to because it's in the second period. Remember that these atoms here have to satisfy the octet rule, or not. For 99% of the cases, they satisfy the octet rule. Okay. Let me draw you This is one resonance structure, one of the Valor-Lewis structures. But these types of molecules, a lot of the polyatomics, have multiple structures that can be used to represent it. So let me draw you another structure called a resonance structure. So this is the first one. The second one, let me draw it like this. So what changed? What changed was the oxygens that have a negative charge. Or you could even say what changed was the location of the nitrogen-oxygen double bond. Now, like I said, a lot of you, or some of you, were saying that, well, when I look at that cover sheet and I see, those three structures, it really just looks like I'm taking this molecule and I'm doing this, rotating it. And then for the third resonance structure, I rotate it again to get the double bond on the right. So, yes, I agree, it does look like that's what's happening, but resonance is different. Resonance is not just taking the same molecule and rotating it. Okay, let me draw the third one, and then let me explain what I mean by that. Because it really does look like all you're doing is rotating the molecule to get the double bond pointing from the left to the top to the right. But if that is the case, then that means that this oxygen is always negatively charged. And this oxygen is always negatively charged. If all I'm doing is rotating the molecule to get these different drawings, wouldn't that charge follow this oxygen as we rotate the molecule? But in real life, what people notice when they do analyses, when they do spectroscopy, is that there's a weird phenomenon, and that is all the nitrogen-oxygen bonds, right? All of them are the same length. Remember in one of the previous videos we said that a double bond is typically shorter than a single bond. Well, if that was the case, if this molecule was static, that every single molecule would have a short nitrogen-oxygen bond and two long nitrogen-oxygen bonds. But in real life, all the nitrogen-oxygen bonds are the same length. That was surprising. Okay, it's not what? It's not one short and two longer. Because what's happening here is that the molecule, the electrons are being delocalized. They're not static, they are moving. Okay? So when you draw resonance structures, and when you draw the arrows to show the movement of resonance, you want to pretend that those atoms are perfectly still. And I like to say, with resonance, atoms don't move. Only electrons. So atoms don't move, only electrons. And let me use this green pen to show you the movement of electrons. It looks like going from the first resonance structure to the second, we made a double bond. So we could bring a lone pair down like this to make a double bond. Now nitrogen at that point doesn't satisfy the octet rule. To resolve that, we move this bond over. So we're literally taking the two electrons for this one of the lines and making it a lone pair. That's how we get from the first resonance structure to the second. So there are three. There are a total of 3 resonance structures. You have to know that. And sure, on the exam, the professor may draw the first one, and ask you, can you draw the other resonance structures, all the valid resonance structures? And then tell them how many resonance structures you have. You have to count the original one as well. So the result of these two green arrows that move the electrons is the second structure. So to get the double bond from the left to the top, again, I am not doing this to the molecule. Okay, that molecule atoms, the atoms of that molecule are perfectly still. All I'm doing is moving electrons. Do you see what's happening now? If that's the case, then at this point, that nitrogen-oxygen bond, the bond to the left, has partial double bond character, partial single bond character. And when we talked about bond order and bond order, we mentioned that a bond order can be 1.5. That's classic 1.5 there. One resonance structure has a double bond, the other resonance structure has a single bond. What is the average of 2 plus 1? It's 1.5. Okay? But nitrate's a little bit more tricky because we have a third resonance structure. Can you see how we get from the second to the third? We have to make a double bond to the oxygen on the right. So we move those two electrons to the bond to make a double bond, and then we have to push these two electrons up. If we didn't push those two electrons up, do you notice that your nitrogen would have 1, 2, 3, 4, 5 bonds, and that wouldn't satisfy the octet rule. Okay? So now we have a third structure. So this is not as easy as saying the NO bond is 1.5, because let's keep an eye on the oxygen on the left. Okay? In one situation, it's a double bond. In another situation, it's a single bond. In a third situation, it's a single bond. Okay? Now think about what's happening. You have this molecule, and the atoms are static, and the electrons are shifting in such a way, shown by the green arrows. Now to get from the third resonance structure to the first, okay, you would bring these two electrons over. But normally on an exam, they don't ask you to go from the last to the first. Just go in order, okay, showing your movement of electrons. If that's really happening, okay, you have to think about all of this happening at the same time, and that the bond between nitrogen and each of these oxygens is what? 33% double and 66% single. Okay. Now, how do we figure out bond order? How to calculate bond order? Because it's easy when half the situation is a double bond, half the situation is a single bond. That's 1.5. But how do I figure out a nitrogen-oxygen bond in nitrate? Well, pick one of the oxygens. It doesn't matter which one. And you see, let's take the left one. You have 2 bonds here, you have 1 bond there, and you have 1 bond there. So you have a total of 4 bonds. But again, you're only looking at one of the oxygens, and it doesn't matter which one. But those 4 bonds exist over 3 resonance structures. So we're taking the average. 4 bonds, 3 structures. That equals 1 1/3, and that's your bond order. Okay, so does that make sense? It's not 1.5 because we have more single bond character. So the bond order is closer to 1 than it is to 2, right? So you could always check, just ask yourself, well, approximately, should it be closer to 1 or 2, or should it be exactly 1.5? Again, double, single, single, the average is 1 1/3. So it's closer to a single bond than a double bond. Okay? So the next thing is to understand in resonance, well, if I had chosen the oxygen on the top, that would also be 1 1/3. If I chose the oxygen on the right, that will also be 1 1/3. That's why they're all the same length. They're all indicative of a bond that's theoretically 1 1/3. 1 1/3. Okay. So I don't know the normal bond length of a nitrogen-oxygen single bond or a double bond, but if I did, okay, I could take that single bond length and multiply it by 1.333 to get the bond length of all of those nitrogen-oxygen bonds. That brings up a little bit of a dilemma because the real molecule is a combination of all three. Okay, so the real molecule is actually a blending, of all three. Because there are 3 resonance structures. If there were 2, then it would be blending of 2. Now, I was going to use the analogy of a mom and a dad having a kid, right? And the kid would have approximately 50% mom characteristics and 50% dad characteristics. Okay, but you notice that the kid is not bouncing back and forth between looking like a mom, like their mom, and looking like their dad. It's not bing, 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 bing. It's not jumping back and forth. It's all the time, 100% of the time, the kid. You got to think of resonance like that. In real life, the molecule is 100% the blending of all three. So this arrow is super important. This is called a resonance arrow. It's not a back and forth arrow. It's a resonance arrow. It's not, some of you may understand, those of you who know a little bit about reactions, understand equilibrium. This is not equilibrium. This is resonance arrow. Equilibrium is, you could say 50% of the time the molecule looks like this, 50% of the time the molecule looks like this. That's not resonance. Resonance is 100% of the time it looks like the blend. So the real molecule is a blending of all three 100% of the time. Okay. So what's the dilemma? The dilemma is, what the heck does a real molecule look like? Right? It doesn't look like the mom. It doesn't look like the dad. It doesn't look like a third person. It's a blending of all three. So that's why people draw Lewis structures, because in real life, the molecule looks like this. And it's not easy to decipher. Here we have one bond and a partial bond. Those dotted lines mean partial bonds. Not only that, you notice that the charge is moving. The negative charge is moving constantly. It's these two oxygens that are charged, next are these two, and next are these two. So what do you do with the charge, right? Well, I don't try to parse the charge. I don't try to say, what would it be actually? It's, you have a -2 over 3. How do we do this? 1, 2, 3, 4, 5, 6. See, I can't even figure out the fraction now. Oh, let's take a look at these, just the top oxygens. So 2/3 of the time it's negative, right? And 1/3 of the time it's neutral. So you would have 2/3, 2/3, 2/3. Chemists don't want to deal with that, okay? If you really want to put a charge, go ahead and put the brackets and say that all the resonance structures always have a 2- charge. Oh, no. We have a plus charge right here. So it's a, sorry about that, it's a 1- charge. This is what the molecule looks like in real life, and you can see how that's a pain, because you're drawing now dotted lines, and you know what? You don't even know if that dotted line is a half bond, or in the actual case, it's actually a third of a bond. So chemists just said, you know what? If you could draw a Valle-Lewis structure, we will accept any one of these three as the Valle-Lewis structure for NO3-, even though in real life you have 1 and a partial third bond for each nitrogen-oxygen bond. Okay, so that's how you figure out bond order, and that's the story of resonance. Let me go through one other example, because I did say that a lot of times your polyatomic ions will undergo resonance. Now, we're looking at resonance right now, but don't go forcing resonance. Not every molecule can have resonance. Okay, most of the polyatomics can. Okay, not all. It's the ones that actually have double bonds and negative charges that typically have resonance. It's the ones where you can move the electron to get another valid Lewis structure. Okay. Let me do carbonate. And you could practice on the other ones. You could practice on sulfate. You could practice on phosphate. You could even do the ites. Nitrite, sulfite, carbonite. But let me do carbonate. And actually, this will be a good test whether you can draw me the Lewis structure. So if you want to pause the video and go through your steps to draw the Lewis structure, when you unpause it, I'll show you how I would do it. Okay, carbon. I'm going to count the valence electrons. 4 plus 3 oxygens times 6 electrons each. It's -2, so you have to add 2 electrons. That's 18, 19, 20, 21, 22, 23, 24. 24 electrons. Carbon in the middle. Oh, I know we're going to do resonance, so let me make sure I'm to the left. Oh, I did this kind of fast. Let me show you from scratch. So you have the central atom, carbon. Okay, and the trick was what? To make all the outer atoms satisfy the octet rule, and then ask yourself, do you have all the electrons? And we do. There's 24 valence electrons, and each of these bonds to oxygen, there's 8 electrons involved. So that's 24 total. But you understand that the carbon doesn't satisfy the octet rule. So also, if I do the formal charge equation, I'll realize that that carbon is positive. Okay, that is not a valid Lewis structure. If it's not a valid Lewis structure, it's not a resonance structure. But it is the first step to get to the valid Lewis structure. So this is not valid. But how do we make it valid? We start shifting electrons. And by doing that, I get this structure here. Okay, don't worry about the angles of the lines. Worry about the bonds and the lone pairs. Okay, do you see how by moving that lone pair to make a bond, all the atoms are still satisfying the octet rule? Well, now carbon also satisfies the octet rule. Not only that, we reduced the number of atoms that have a charge, which is stabilizing, right? We got this oxygen and carbon to be neutral. This is the first resonance structure. Okay, now your classmate could have drawn it with a double bond to the left. Another classmate could draw it to the double bond on the right, and that would be their first resonance structure. But just by chance, I picked the oxygen on the top, first resonance structure. And that's perfectly fine. If I ask you to write the Lewis structure of carbonate, this would get full credit. But then I or your professor could ask, draw all the resonance structures and show how you get from one to the other. So we're doing the same deal for this. Okay. Yes, it's just coincidence that I picked a molecule that had 2 negative oxygens, but now it's a -2 charge because the central atom, carbon, is not charged, but here it was charged. Okay, so I'll do this kind of fast. Second resonance structure would be this. Okay, And then the third resonance structure would be the double bond on the right. Okay. This is not easy, and I'll even say that this is not intuitive. Although it does follow pretty simple rules to understand, applying those rules is not easy. You're going to have to practice, especially moving these electrons and understanding when a double bond is made and when a double bond is broken. Okay, not the full double bond, but just one of the bonds of the double bond. Okay. Just make sure I don't want to be sloppy or too sloppy. Those are the three resonance structures. So carbonate has three. Carbon has three. This one is not valid, but it is a good step to get to a valid Lewis structure. So yeah, this is on my scratch sheet of paper. The bond order between carbon and oxygen, again, will be 1 1/3. Because if we take a look at, let's take the top oxygen. 1/3 of the time it has a double bond, 2/3 of the time it has a single bond. And what equation are you using? Again, the number of bonds for that particular oxygen. Okay, so only pick one oxygen, and then it's spread over three structures. I'm not going to do these with you, but let me give you some example problems. Nitrite. Nitrite is NO2 minus. What the exam problem could say is that this is one structure of nitrite. Or they may even ask you to draw the structure of nitrite. Draw all the resonance structures for this molecule. Now, it could be just two. For the two examples that we saw, there were three resonance structures. Okay, so draw all resonance, and this is one of them. Let me show you phosphate, or at least draw the first resonance structure for phosphate. So this is going to be tricky. You have P, O, 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 O. You could get the central atom, phosphorus, to not be charged by making one of these a double bond. Now, I did that without going through all the steps, right? I didn't count the valence electrons. I didn't add more electrons to the central atom if I was short. I didn't move electrons. I didn't show the movement of electrons. But this is a valid Lewis structure for phosphate. Same thing, draw all the resonance structures. So you'll have at least one, the first one. You'll have another one. And I'm telling you here that you should have, well, I'm not going to tell you. You'll have to find that on your own. But you're drawing all the valid Lewis structures, okay? Just like here, it took us three structures to draw all the valid Lewis structures. Or you could say all the valid resonance structures. The thing is, if I drew a fourth one, it would look exactly like this, probably. I'll just start repeating myself. Okay, so take a look at that. Take a look at that. I could tell you now that neither of these has exactly three resonance structures. Okay? So they're different from the examples that we saw for nitrate. Whoops, nitrate and carbonate. All right, good luck. Try these two molecules. Draw all the resonance structures for those, and determine the bond order. And they're all going to be the same. Well, the nitrogen-oxygen bond. So whether you look at the oxygen on the right or the left, the bond order will be the same. And obviously for this one, you're looking for the bond order for the phosphorus-oxygen bond. They'll all be the same, just like we saw for nitrate.